Unit Operation Classroom. Today we are going to discuss Cauchy Euler differential equation solution. Okay, we'll see what is Cauchy Euler differential equation, and my name is Shikhar Bhattacharjee. Consider the differential equation. So this is a differential equation which is given. So this is a typical Cauchy Euler differential equation. We'll see why it is so. So anyway, this of course can be written as this one because y double dash can be this can be written as y double dash. This can be written as y single dash. 3y is equal to 0. This is a standard notation we use. X is equal to 1 at a certain point of the general solution. We see y is equal to 3 and this derivative is equal to -5. What are the key concepts used in solving this problem? Recognize, first of all, which one is a Cauchy Euler form of second order ODE. How to do that? Then we have to use the power law. That's a trial solution, which is used to obtain the characteristic equation. Then we identify the general solution from the roots of the characteristic equation, and we apply the two given initial conditions to determine the general form of Cauchy Euler equation is given by this, where this is equal to A is a constant, B is a constant. This, of course, can be written as y double dash. This can be written as y single dash. Okay. For such an equation, assume a trial solution. This is a very standard for this is a Cauchy Euler equation. We'll see how it differs from the standard ordinary differential equation with constant coefficients, which how that differs and how to identify and recognize that this is a Cauchy Euler equation. We'll see that. So for Cauchy Euler solution, so this is a typical trial solution which we use. Then, of course, the first derivative would be this, and the second derivative would be, of course, equal to this. Then we substitute in this given differential equation here. We put that and we get this one as like this. Of course, x to the power n cannot be equal to 0 for x greater than 0. So this is my characteristic equation. This is a quadratic equation, and we solve and we get two roots, 1 and -3 in this particular case. So for Cauchy Euler equation, the general solution depends on the nature of the roots of the characteristic equation. So if you have like two distinct real roots, case 1, then of course we get this is the solution. For case 2, when we have repeated real roots, that means the two roots are equal, then we get this solution. And case 3, where we have complex conjugate roots, so this is the solution. So in our case, of course, the values of m1 is equal to 1 and this is equal to -3. So these are two distinct real roots. So this is the applicable general solution. Okay. So we use this one right here. So C1 at this one right here. And of course, we use these two conditions which are given at x is equal to 1, y is equal to 3, and at x is equal to 1, the derivative given. So we use these two conditions here to get the values of C1 and C2. So these are all given in this website here. So we get the value of C1 is equal to 1 and C2 is equal to 2. So this is my general solution here. Okay. This is my particular solution. Once we know the values of C1 and C2, which is calculated right here. So therefore, it now is very easy. At x is equal to 2, this will be the value. So this is my answer. So the answer to this problem is, of course, 2.25. So this is the answer is 2.25. Okay. Now, let us see slightly in little more details. What are the key learning concepts here? Distinguishing two types of ODEs. That's critical. Learn to distinguish between two types of ODEs. What are they? The first one is second order linear ODE with constant coefficients. So these A and B are constant, and this, of course, is second order ODE. Okay. And what is the second order Cauchy Euler ODE? That, of course, is here we have x squared. That means the square of the independent variable, and here is the x of the independent variable. Okay, so this is for with constant coefficient. That's the way. And for Cauchy Euler, of course, just see here an x square comes in. X square comes in here, and x comes in. That makes it Cauchy Euler. So you have to identify and recognize. So I've just given a comparative table here. So for that, the general form is like this for constant coefficient, and for the Cauchy Euler, as we have discussed, this is the Cauchy Euler type of ODE. Trial solution, in this case, we use y is equal to the power mx, we'll see. And for here, the trial solution y is equal to x to the power n. Once we do that, we get the characteristic equation, a quadratic equation like this. Whereas in case of Cauchy Euler, we get this as a characteristic equation. If the roots are real and distinct, we get this as the general solution. And for Cauchy Euler, this is the general solution. If we get two equal roots, this is the general solution. For constant coefficients and for Cauchy Euler, this is the general solution. And for complex roots, these are the solutions. Okay. So the main thing is to identify whether this is an ODE, second order ODE with the constant coefficients or the Cauchy Euler type. Okay. Now, just to make it more clear, so you see our given Cauchy Euler equation is this, right? And these are the conditions which we have given, and we have got the answer at x is equal to 2, y is equal to 2.25. Now, for comparison, if we have to derive an analogous second order ODE with constant coefficient, this is Cauchy Euler. So if it's an analogous, if you want to do second order ODE with constant coefficients, of course, this will not be there, this will not be there. So this is the equation, okay? And let us use the same initial conditions. So here we put y is equal to e to the power mx as the trial solution. And of course, first derivative is this, second derivative is this. These are all given in the website. So, of course, this is what we get, and we know e to the power mx can never be equal to is 0 and is always positive. Just an example, e square is this value, e to the power 0 is this value, if to the power negative 2 is such small value, to the negative 10, we see what a small value. So, even when the exponent becomes strongly negative, the exponential may approach 0, the exponential may approach close to 0, but it never actually becomes 0. Okay. So this is my characteristic solution here. Why did we discuss? Because this can never be equal to 0. So this has to be equal to 0. So that's my characteristic equation. So from there, we find out the values of the two roots here. Remember, now we are solving an ODE with constant coefficients just to show its difference between constant coefficient and Cauchy Euler type of ODE. Okay, so this is very easy. So this is a general solution. We use the conditions here, y1 is equal to 3 and this value. So if we do that, then we get this is my general solution. And at y2, it is equal to 3.10. Whereas for Cauchy Euler, the value, remember, was 2.25. Okay, so what are the practical chemical engineering applications of this particular problem? In heat transfer, steady state, let's say one-dimensional, constant thermal conductivity, no internal heat generation. This is a typical second order equation with respect to temperature we get. So this is, as for example, heat transfer through furnace walls, flat slab or thin wall we get. So this is an equation with constant coefficients. So this is a typical linear type of temperature profile. And this is again this is a second order. This is a second order ODE with constant coefficients. Here, of course, A is equal to 1 and B, of course, is equal to 0. There is no first derivative, and C, of course, is also equal to 0, right? So this is a second order ODE with constant coefficients. Similar, if we, the steady state radial conduction through a spherical shell, if we do that, this is the equation what we get. And of course, if we just expand on it, this is 1 over r squared. This, of course, is going to be equal to r squared, the second derivative of this one, plus, of course, 2r dt over dr. And if we divide by r squared, so this is what we get. So as you can see, this is the equation what we get. This is a typical Cauchy Euler type of ODE. Why? Because Cauchy Euler type of ODE, here you see A is equal to 1 in this case. So here, this is my independent variable. So this is my x squared. And there, this B is equal to 1. And this is, B is equal to 2 here. B is equal to 2. And this is, of course, R right here. So because this independent variable is R. And of course, C is equal to 0. So this is a typical example of Cauchy Euler type of ODE. And this comes when there's a spherical coordinate system. And heat transfer to a spherical coordinate system. So as you can see, again, this is a non-linear temperature distribution here. So similarly, we get analogous equations for mass transfer. For steady diffusion through a planar layer, constant diffusivity, we get this type of equation. That means this is an equation with constant coefficients. Now, this could arise in case of diffusion through a thin membrane, stagnant gas film, liquid film near an interface, or a planar catalyst layer. So that's where we get this type of concentration distribution. Okay. Whereas we can get same kind of if there is a diffusive mass transfer through a spherical coordinate system, as for example, diffusion through a spherical shell, droplet, particle, or capsule, and there should be, of course, no reaction within the spherical shell. That's very important. That term is not here. So then it is a very simple one, and this is an example of Cauchy Euler type of ODE. Value of here, of course, is 2.25 at x is equal to, this is the answer.